Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on nitrogen compounds. So this is topic 34 for the CIE specification. So this is the Cambridge Internationals. Obviously in this video we're going to be looking at nitrogen based compounds, so looking at amino acids and proteins, amides, amines, a little bit of electrophoresis as well. So there's various different things in this topic. This is not the only topic. Obviously, this video is going to look through topic 34, but I've got the full range of topics for year 1 and year 2 chemistry. So this is topic 1 all the way to 37. So if you're studying CIE, then this is the perfect place to be to get all your information for your particular exam board. The full range is obviously on Allery Chemistry YouTube channel. Please hit the subscribe button, and you'll get all the updates on videos that are being uploaded. And also these slides here are available as PowerPoint slides, and you can purchase them from my test shop. The link is in the description box below, but they're perfect to supplement your revision notes. You could print them out and put them in your files and write notes on them, etc. So everything you see here is available in hard copy if you wish to have it as well. Okay, so let's make a start and look at what we mean by nitrogen compounds. Now you'll see the way CIE structure this is you'll find that the year 1 topics will have similar titles to the year 2 topics. In fact, the vast majority of them are exactly the same. So what they try and do is split up nitrogen compounds for year 1 and can build up on the knowledge that you've learned in year 1 into year 2. So what you'll find here is there'll be a requirement for you to understand some basic nitrogen compounds, things like amines, ammonia, ammonium, etc., which was found in year 1. And you'll also find this kind of merges with other topics in year 2 as well. There seems to be quite a bit of overlap. So you might see some bits and pieces on here that you might have seen in previous topics too. So it's really just to try and bridge it and show kind of the bigger picture, because obviously although these are broken up into isolated topics, in reality chemistry is quite broad and will kind of cover other topics as well. So hopefully it just kind of allows you to see the bigger picture and makes it a bit more tangible. Okay, so let's start with the first one then, which is amines, and this is a chemical that you would have seen in year 1 anyway, but an amine is derived from ammonia molecules, and obviously ammonia molecules are NH3. They all contain a nitrogen atom, and hydrogens are basically replaced with an organic group instead. So this could be an alkyl group, for example. So we get loads of different types of amines. You get primary, secondary, tertiary, and quaternary amines. So let's have a look at some of them here. So we've got methylamine, which is a primary amine, and you can see that's the structure of it there. So it looks a bit like an ammonia molecule. So ammonia would be NH3, but instead of one of the hydrogens has been replaced with a methyl group. Your secondary amines, for example, dimethylamine, basically have 2 methyl groups in this case, but it's substituted the second hydrogen on the molecule. Tertiary is trimethylamine, you can see there. So we've got 3 organic groups that are now surrounding the nitrogen. And then quaternary is tetramethylamine ion. So basically you've got 4 methyl groups surrounding nitrogen, but because nitrogen can only really bond 3 times to form a stable compound, to form a stable kind of setup, so follows the octet rule. Then, because it's got the extra bond here, we have a positive charge in here. So this is an ion. So this is tetramethylamine ion. Okay, you can also get phenylamine as well. You will have seen phenyl groups or benzene in earlier topics prior to this as well. So this should be fairly familiar to you anyway. So these are non-aromatics, these first 4 here, and they're called aliphatic amines. Again, you probably heard me use that term before. So there's 2 broad categories. Aliphatic just means molecules that don't have a benzene ring, basically. And aromatic amines are ones with a benzene ring in here. So phenylamine is classed as aromatic. Okay, amines are primarily used as bases. So they have a lone pair of electrons, and that allows them to accept a proton. So remember, Bronsted-Lowry bases are proton acceptors, and obviously they act as a base. So basically, that lone pair of electrons allows them to form a dative covalent bond with a proton that it will accept. And obviously, both electrons in the bond originate from the lone pair on the nitrogen. So you remember that from year 1 when we looked at structure and bonding. So here it is here. So there's your primary amine, as you can see there. It's got the lone pair of electrons of nitrogen. This can accept a proton and form this dative covalent bond or coordinate bond with the proton. And overall, you end up with a positively charged ion. Now, the strength of the base is actually very much dependent on the availability of the lone pair of electrons on the nitrogen. And obviously, the higher the electron density in there, then the more readily available the electrons are. So, and obviously, this depends on the type of molecule or the type of group that is attached to the nitrogen as to how strong this base will be. And that's exactly what we're going to look at here. So the order of the base strength is as follows. So you've got your aromatic amines, so that's one with the benzene rings, are the weakest base. Then it goes to ammonia, and then it goes to primary aliphatic amines as moving towards a stronger base. So let's have a look at some examples here. So here you've got your phenyl amine, as you can see here. You've got your lone pair of electrons on the nitrogen. Now what the benzene ring does is it actually withdraws. Benzene is a withdrawing group. So what it does is it pulls electrons away from the nitrogen into this ring structure because it tries to keep it stable and delocalized. And so what this means is it actually reduces the availability of this lone pair of electrons to accept a proton. And if that's reduced, it means it can't act as a base as well. So it's a weaker base. And obviously you can kind of see the kind of clouding here. The yellow clouding here shows where the electron density is. So it's been moved into the ring. Now with ammonia, you can see with ammonia, it's just kind of sat in the middle. So it's more readily available than it is with phenyl amine. And then alkyl groups, so for example in a primary amine, they actually push electrons towards the nitrogen. And this means that the density on the nitrogen, density of electrons on nitrogen actually increases. And this means that the availability of the lone pair of electrons on nitrogen will also increase. And that means it is more readily, it's going to accept a proton much more readily. And so therefore your primary amines are therefore a stronger base compared to these ones here. Now you need to be able to, there we are. So amines are also nucleophiles as well as bases, and you will have seen that in previous topics as well. You need to be able to explain the reasons why your aromatic amines are weaker bases and your primaries are stronger. So make sure you're talking about electron density and the availability of the lone pair of electrons on the nitrogen to accept a proton. Okay, so let's have a look and see how we can make aliphatic amines. So aliphatics are basically molecules that don't have a benzene ring in, essentially. So aliphatic amines are made in two ways. We can either react a halogenoalkane with excess ammonia, which we're going to look at first, or we can make them by reducing nitriles instead. So like I say, we're going to look at reacting halogenoalkanes with excess ammonia first and look at the kind of mechanisms here. So in this example, we're going to use chloroethane as the halogenoalkane, and we're going to react this with excess ammonia. Now you will have seen this in the halogenoalkanes topic in year 1. Obviously this is linking, this is basically just kind of covering some of that older information in year 1 and bringing it and adapting it to some of the concepts of year 2. But there's no harm in talking through it. So you've got your lone pair of electrons on your nitrogen. So this is going to be ammonia. Now here it's going to act as a nucleophile because it's got a lone pair of electrons, and it's going to go for this delta positive carbon. Make sure you're writing your delta positive and delta negatives on these mechanisms here. So the arrow, there we are, is going to go into that delta positive carbon. It's going to form a bond, which is then going to subsequently break the carbon-chlorine bond here. Okay, so this is a nucleophilic attack. And we form an intermediate. So we have the NH3, which is on here. Now that's bonding to 3 hydrogens and the carbon. We have a positive charge on that nitrogen. Okay, so they've got this alkyl ammonium salt that's been formed, and the chloride ion is then being released. So we form our, we're basically just drawing this back out again just to kind of separate out and show you in the displayed form with all the bonds. We have this excess ammonia though, so we have another ammonia molecule that's floating around here. This has a lone pair of electrons. Now this time, this ammonia is going to act as a base instead, and it's going to go and target the proton, okay, one of the hydrogens on the side here. And then the electrons in this bond is then going to jump into the nitrogen to stabilize that positive charge, and then you're going to end up with this product, which is a primary amine, okay, and we form ammonium chloride as a salt too. So just make sure you're aware of these mechanisms and know how to draw them. Okay, notice we need 2 molecules of ammonia. This is why the word excess is important, because 2 molecules, one acts as a nucleophile at the start here, one acts as a base in the second bit here. So now one of the kind of issues here is that actually with each step we're going to, we've produced a primary amine there, but that primary amine can also then go on to react with more halogenoalkane and produce secondary amines, and then produce tertiary amines, and then produce quaternary ammonium ions. So the mechanism obviously for making each amine is similar. So instead of using 2 ammonia molecules that we'd seen just before in the previous mechanism, we're going to use 2 amines instead. So that primary amine still has a lone pair of electrons. If anything, it's more powerful base, more powerful electrophile, should I say, than the other ones. So this can then go in and attack a halogenoalkane and form a secondary amine, and then that can then react with the halogenoalkane and form a tertiary, and then a quaternary. So what you're getting here is obviously in this case you've got a primary amine here reacting with the halogenoalkane, and that will form this structure here. This is your secondary amine, plus your salt is also produced as well. So this is an example of obviously how you can get this kind of successive reactions. It's not just the ammonia that will react, it's also the products that you've actually made will also react with the halogenoalkane. Okay, so using this method, as you can see, can have a downside. So in the mechanism, obviously we saw the production of a primary amine. However, like I say, this produces the secondary, tertiary and quaternary salts, and actually we end up with quite an impure product. We're not just, if you're in the industry of producing a primary amine, this reaction is not really massively controlled. It will kind of produce other things. So obviously the primary amines still have a lone pair of electrons on, they act as a nucleophile, and they'll keep on reacting to make them other products as well. So just to make sure that you're aware of that. So this method, although it does produce your amines, it produces a mixture of them, primary, secondary, tertiaries and quaternaries. So the other way of getting around this is actually by reducing nitriles instead. And so here we're going to look at reducing nitriles using a nickel catalyst and hydrogen gas. So this is the cheapest way to make primary amines in industry. It uses hydrogen, like I say, and a catalyst to help reduce the energy required. Now, this reaction is called catalytic hydrogenation. So hydrogenation is adding hydrogen to something. So unlike using your halogenoalkanes, like we've seen before, this reaction produces primary amines only. So we're not getting your secondaries, tertiaries or quaternaries, any impure products. So if you are making primary amines, this is the reaction we need to proceed rather than the other one. And here's the reaction here. So you've got your nitrile, which is CN. That reacts with your hydrogen, as you can see there, using your catalyst, high temperature and pressure, and then we form our primary amines. You don't get any other kind of impurities that's formed. So we're going to look at another one as well. So this is using a reducing agent instead and dilute acid. So this method, like I say, is more expensive than using hydrogen gas and nickel or platinum. Lithium aluminium hydride is an expensive reducing agent, so it's not really used on an industrial scale. It's just a different method of producing a primary amine by reducing nitriles. Here we're going to use the square bracket H to symbolize your reducing agent, and this is dissolved in a non-aqueous solvent. This could be, for example, dry ether. So it's just another way of producing your primary amines. We're going to use a reducing agent instead. Like I say, this method isn't really used in industry. It is much more expensive than the other method that was shown you before. Okay, so let's see how we make aromatic amines in. So they were all aliphatic amines, so in other words, molecules without a benzene ring. So now we're going to look at, well, how do we make them with a benzene ring? So aromatic amines are actually made by reducing nitro compounds, such as nitrobenzene. And aromatic amines are used to make dyestuffs, which you've seen a little bit of previously, but we're going to go into a bit more detail in this video on how they're actually made. And pharmaceuticals, so they're incredibly valuable as a raw feedstock. So the first thing we need to do is we need to heat under reflux nitrobenzene, and we heat that with some hydrochloric acid, obviously strong, so concentrated hydrochloric acid, and some tin, and we form a salt such as your phenyl ammonium chloride salt. So here you can see we've got your nitrobenzene, your reducing agent, which is here under reflux with your HCl and tin catalyst. And then the second step is then we take the salt that we've produced here and react it with an alkali such as sodium hydroxide. So that's the second step. And therefore we'll produce our aromatic amine, which you can see there, that's phenylamine, and you produce water. Now this whole thing is done under reflux, and it's this chemical here that will then be used to produce your dyestuffs, which we'll see later, and pharmaceuticals. So a really valuable reaction, obviously for obvious reasons. Okay, so let's have a look at some further reactions of aromatic amines. So we've produced the aromatic amine. Let's have a look at some kind of general reactions. So phenylamines, they can actually react with bromine water. So there's your phenylamine reacting with bromine, and it will brominate 3 times. You get multiple bromination. So we've got bromine on the 2nd, 4th, and 5th carbon, as you can see there, and we produce 3 HBr. Now what we'll observe is a white precipitate. So this is your white precipitate of 2,4,6-tribromophenylamine, which is what this compound is, and we'll see that fairly quickly. So it reacts relatively easily. Remember, if you try to do this with benzene, which you will have seen in the previous topic, you would need a halogen carrier to get this working. But because you've got an amine here, it kind of weakens the ring structure a little bit, so the bromine can add with relative ease to this compound. Okay, so like I said, one of the uses is to make azo dyes. Now, azo dyes, these are man-made dyes, and they're made from aromatic amines that we've just seen there, and they contain the azo group, which is the NN group, as you'll see here. Now, these look quite complicated, and they are quite big molecules, but incredibly vital, obviously, for dye stuffs, for fabrics, for paints, mainly obviously for fabrics, but also for using dyeing plastics, for example, so making, say, coloured furniture and things like that. So the majority of azo dyes, obviously the majority of these are used in fabrics. This is where they're obviously used all the time. So the majority of azo dyes are actually made up of an azo group linking the benzene rings together, and we can see the structure of a typical azo dye here. So you can see you've got this NN group linking 2 benzene rings together, and this is very typical of an azo dye. So azo dyes, they're relatively stable molecules because you've got this delocalized ring system here. This extends into this azo group, and obviously that's pretty useful for dyeing fabrics. What you don't want is the colors from your clothing just to kind of to fall apart or to change color completely. I mean, sometimes they do fade over time, but what you don't want is that to happen instantly or to kind of break down in colour if you leave them out in the sun, for example. So this benzene ring gives it incredible stability and kind of holds the colour within the garment. So dyes, like I say, are colourful, and the reason why is because light is absorbed by the delocalized electrons, and this varies depending on what amines and aromatic groups we're using to make the dye. So the light is effectively being absorbed by the electrons in these ring structures, and this gives you these lovely coloured fabrics, as you can see on here. Okay, so this is obviously chemistry. We can't just look at some coloured fabrics. We've got to understand how these things are made and what we can do with them. So azo dyes, they're made by a coupling reaction. And actually we make something called the diazonium salt first, and then we couple it with a phenol. Now, you will have seen a very, very brief introduction to this in the phenol when we looked at the hydroxy group topic for year 2, when we looked at phenols in a little bit more detail. Here you're going to go through a lot more information because obviously it's to do with nitrogen compounds, this topic. So the first thing, we've got to make the diazonium salt first. Okay, so the diazonium salt is made by reacting nitrous acid, hydrochloric acid, and phenylamine all together. Okay, but what we have to do is make the nitrous acid first. Now, the problem is nitrous acid isn't very stable. Okay, it's quite an unstable compound. So the actual making of nitrous acid is actually all done in situ. Okay, so it's made within the actual reaction. But the reaction here is you make, effectively, you have to kind of isolate this reaction. You make nitrous acid by taking sodium nitrate, which is this one here, reacting with the hydrochloric acid that's in here already. And then we form nitrous acid, which is HNO2, and sodium chloride. Now, like I say, it is unstable, so it's all made in one pot. You're not exactly making this in a separate beaker and then adding it into the vessel. It's being made through the reactions that you're making here. If you made it separately, it would just decompose. It wouldn't hold as nitrous acid. So effectively, nitrous acid is then made in this reaction, and then as soon as the nitrous acid is made, it reacts with hydrochloric acid that's in that vessel and your phenylamine, which is this here, and it forms your diazonium salt, which is this here. Okay, and we form some water. So that's the salt, and this is going to be the active kind of ingredient to help make our azo dye. Okay, so this one's called benzene diazonium chloride, this one here. Okay, now this has all got to be done below 5 degrees. Okay, if it's not, then we end up making a phenol instead, and we don't want the phenol, we want this. Okay, so it's really important we keep this as cold as we possibly can. Okay, so step 2, once we've made our diazonium salt, we've then got to make the azo dye. So what we do is we add phenol to sodium hydroxide to make sodium phenoxide. Okay, that's what we need to do. And then we add that diazonium salt, the benzene diazonium chloride, that's the salt, is then added. And again, it must be sat in an ice bath. We've got to keep all this as cool as we can. So phenol is a coupling agent, and it has a high electron density, as you will have seen in the, like I say, in the hydroxy group topic, where we looked at phenols. If you're not sure what I'm talking about here, please go and see that video for year 2. But the phenol is obviously a benzene ring with an OH group attached to it. And effectively the electrons in the OH group integrate within the ring, so you form this kind of delocalized, distorted delocalized system. And what this means is phenol actually, having a phenol attached to it means that the attack on the phenol is more susceptible at carbon 2, 4, and 6. And this is susceptible to attack from a weak electrophile, which in this case is going to be your diazoniamine that we've just made before. Okay, like I say, make sure you go back to that topic if you're not sure what I'm talking about here. So I'll go through it in a lot more detail there. So the azo dye produced precipitates out really quickly, and we get this lovely orange precipitate that's formed. So here is your phenol, there it is, and we're going to react it with our benzene diazonium chloride salt, which is this here, with a bit of sodium hydroxide, and there we formed our azo dye, which is there. So there's your phenol, and it's obviously added on here on the 4th carbon and coupled with the salt, as you can see on there, and then we form sodium chloride and water as a product. So this is a bright orange one in this example here. So you can see, quite complicated reaction, but just make sure you understand the steps on making azo dyes. Okay, so amides, these are derivatives of carboxylic acids. They have the functional group of CONH2. Again, you would have seen some of this in a previous topic, just briefly. Obviously here we're going to go into a little bit more detail. So an amide looks a little bit like a carboxylic acid. So here you'd have OH for a carboxylic acid, but with it being an amide, you have NH2 hanging off the carbonyl group here, and that's what we mean when we say amide. You can get, there we are, there's your NH2. You can get N-substituted amides, and this is where instead of having a hydrogen, you have a R group, so an alkyl group that's substituted instead. So the substituted bit is whatever this group is, whatever R is, and that's substituted on the nitrogen in an amide. Okay, so that's normally an alkyl group. So you would have seen this previously in topic 33, where we looked briefly at acid chlorides reacting with primary amines to form these N-substituted amides. And here we are. Okay, so we're going to use these acyl chlorides that we've seen in topic 33, and this is where there's a bit of overlap here. So there's your acid chloride, and we react that with an amine. We react that with ammonia. So this is ethanol chloride reacting with ammonia, and you form your amide. So this is one way in which you can make an amide. An incredibly vigorous reaction. White Mr. fumes produced, obviously with hydrogen chloride being made. Not great to breathe in, so this should be obviously done in a fume cupboard. Hydrogen chloride is incredibly acidic and not good for you, so definitely don't breathe that in. Another way, obviously, of producing N-substituted amides, as I alluded to before, is to again use an acid chloride and react it with a primary amine this time. And here you form your N-substituted amide. So in this case, the substituted bit is the methyl group. So this is N-methyl, there we are, ethanamide, which is your ester here, your N-substituted, not ester, N-substituted amide, okay, which is produced here. Again, a really vigorous reaction, and hydrogen chloride fumes are produced. Okay, so amides, they can be hydrolyzed using an aqueous alkali or an aqueous acid. So hydrolysis is basically the breaking of a molecule using water. Okay, so you're using aqueous-based, you can use alkali, so base hydrolysis or acid hydrolysis, but they're obviously all dissolved in solution. So here's your amide here. Okay, amide can be, obviously this is broken down using an aqueous solution of acid. Okay, so aqueous acid, and if we do that, we produce a carboxylic acid plus ammonium chloride. So this is what it is if you react it with an acid. Now, if you react it with an alkali, we get a sodium salt. So here we've got sodium ethanoate, which is this compound here, plus ammonia. So you need to know about the hydrolysis of amides using an acid and using an alkali, and be able to write these reactions. So that's really important. Okay, so the reaction with an alkali is a good test for an amide because we can actually detect ammonia. So if we wanted to check to see if we have an amide present, we can add this alkali, and if we get ammonia produced, we can obviously test for it using litmus paper, or you can smell it. It's got a very pungent smell of ammonia, but here obviously you use litmus paper, and ammonia is a base, so you get a color change on your litmus paper. Okay, so amides can be reduced as well by using a reducing agent, and you've seen this reducing agent quite a few times. So this is lithium aluminium hydride, LiAlH4, and you can see here that we've got our N-substituted amide here, okay, which is this one here. So this is N-methyl propanamide, as you can see, because you've got ethanamide, because you've got two carbons. So this one, we're going to react it with a reducing agent and some water, and we produce our reduced product here, as you can see. So the carbonyl group has effectively been reduced at this point, and we produce this product instead. Okay, so this reaction proceeds in ethoxyethane solution, and this is the reaction. So what we're doing is reducing this down to this amine instead. Okay, so amino acids. Now, for all you biologists out there, this bit's a bit of biochemistry for you for the kind of last section of this video. But amino acids actually have an amino group in there. No surprise, because it's got amino group, so it's NH2, and a carboxyl group as well, which is COOH. So there's a classic example of an amino acid. So there's your carboxyl group and there's your amino group on the other side. So amino acids are what we call amphoteric. Okay, so it means they have acidic and basic properties. So they're quite versatile as a molecule. Now, amino acids have an organic side chain and they're represented with an R, and you can see here. So they'll have an organic side chain, maybe an alkane, for example, with the exception of glycine, where R is actually just a hydrogen instead. So glycine, that would just be hydrogen. So amino acids, like I say, except glycine, are chiral molecules. So remember that from previous topics, because they have 4 different groups surrounding them. And that means they can rotate plane polarized light. Remember, that's one of the signs of having something that's optically active, is that if you put it through, if you pass plane polarized light through an optically active compound, it will rotate the plane polarized light to one side. Okay, so amino acids sometimes exist as zwitterines, and this is where anybody who studies German will probably know what this means. So a zwitterine is basically a molecule that has both a positive and negative ion. Okay, so zwitter meaning double, I believe. So zwitterines basically got a double ion, and they only exist at the amino acids what we call isoelectric point. Okay. So the isoelectric point is basically the pH at which the average overall charge is 0. And this is obviously dependent on the R group that we talked about before in the amino acid. So here we've got a zwitterine is likely to be formed when the pH is at the isoelectric point. And so both the carboxyl and amino groups are ionized. So you can see here that you've got your amino group here, which has got the positive charge, and the carboxyl group has got the negative charge. So at the isoelectric point, which would be at a specific pH, then some amino acids will form, well, if an amino acid is at its isoelectric point at a specific pH, then it will form this zwitterine, depending on obviously what the R group is. The R group will change the isoelectric point for each amino acid. So at low pHs, so in this case, if there's a pH is lower than the isoelectric point, then the C double bond O minus is likely to accept a proton. So obviously the proton will add on to the negative, and you'll form this. So this is the molecule or the amino acid that you would see at a low pH. And at a high pH, you're likely to see this. So high pH is obviously they're alkaline. So these are likely to give up a proton, as you can see here, and obviously form the NH2 group instead. So this is at the isoelectric point. This is your zwitterine, so 2 ions, double ions. At low levels, low pH is going to be this. At high pHs, it's going to be this. Now, the isoelectric point, like I say, it can be different for different amino acids. Okay, so we've looked at amino acids. Now, amino acids are obviously building blocks, and amino acids can be used to make proteins. And you'll see later in the topic after this, which is topic 35, when you look at polymers. But proteins are polymers, and they're made up of amino acid monomer units. So they're the individual blocks that make up the polymer. And they're a type of condensation polymer, which you're going to learn a lot more about in topic 35. But for the purposes of this, proteins are just amino acids joined together, and the link that joins them is called a peptide link. And like with other condensation polymers, the chain can be broken through hydrolysis, so we can break it down, which is breaking using water, remember? Hydro meaning water, lysis meaning to break. And so when we join 2 amino acids together, we form a dipeptide molecule. So let's have a look. So here we've got 2 amino acids. We've got amino acid 1 and amino acid 2. And so these are the standard amino acids here. And we've got an R group and we've got R1 here. So these can join together, like I say, to form your dipeptide. So what happens here is the NH, the hydrogen from here, drops off, and the water from here drops off, and that combines to make water. Okay, there it is. Okay, so that's removed, and water is produced, water is eliminated. And then what we form is the residual bond then joins together to form this dipeptide link. So we've joined the two amino acids together, and this is the beginnings of a protein. Water is eliminated because it's a hydrolysis reaction. Okay, so we're splitting that out. So it's also a dehydration reaction or elimination. So we're eliminating this water molecule here. And that's effectively a protein. Okay, there we are. Condensation moving forwards. Hydrolysis going backwards. Okay, so hydrolysis is obviously breaking up the protein, as you can see there, to form the individual amino acids, and condensation moving forwards because water is being eliminated. So the dipeptide has a COOH and an NH2 at the end, okay, as you can see there. So you've got your COOH and your NH2 at the end. And so then further reactions can actually take place to make the longer polymer chain. And the protein can be broken down into amino acids via hydrolysis, as I mentioned before. You need severe conditions to break this down. So you need 6 molar hydrochloric acid, 110 degrees Celsius, and reflux for 24 hours. So proteins are incredibly strong polymers, really, really strong polymers. And actually, if you look at, for example, your hair is made out of like types of protein chains, it's really difficult to break hair down, really difficult. And you need some quite corrosive chemicals to try and break it down. So if you get hair, say, kind of stuck in a plug hole, for example, and it's really difficult to get rid of, you need to pour normally something like a caustic solution, something like sodium hydroxide, potassium hydroxide, really concentrated, put that down the plug hole and leave it, and it starts breaking down this polymer chain. And effectively what you're doing when you're putting these chemicals down is you're undergoing a hydrolysis reaction to break the peptide link. So you can understand how kind of hard, how difficult that is to break a protein down. So to determine the amino acids that we used to make the protein, we break the bond in the middle of the peptide link. So we basically break this bond here in the middle of the peptide link, and then left and right will tell us the types of amino acids that are produced. And effectively all we do is we add OH and H to each one of these, and then that will tell us the obviously individual amino acids that we used to make the protein in the first place. Like I say, you're going to see a lot more on condensation polymerization in topic 35, and we look at a few more examples such as terylene, nylon, for example. So we'll look at other examples in that topic. Okay, so electrophoresis. Okay, so this is a method in which we can separate amino acids, okay, and we use something called electrophoresis to do this. And as you've probably guessed, it contains the word electro in there, so it's obviously got something to do with electricity. So here's the setup of what this looks like. So we have a power supply. This is a DC power supply. We have a glass slide in the middle, and there's a mixture of amino acids kind of put on the slide. There's a little blob of it on there. We have an electrolyte in the tray here, and we have filter paper which is saturated in a buffer solution. So this is the setup of electrophoresis. Now I've just put this on here just so you can see what's happening. I think sometimes it's easier if we have a visual picture of it. And as we've seen, we know what zwitterions are. They exist in amino acids, and depending on the pH of the solution they're suspended in will depend on the type of ion that we have. So remember, your zwitterion exists at the isoelectric point. At lower pHs, obviously, you have your carboxylic acid that's formed, and at higher pHs, you have NH2 that's formed at the other end of the amino acid. So if we apply this to a mixture of the following amino acids, let's say glutamic acid, glycine, and lysine in a solution of pH 7, okay, so the buffer is there to kind of keep that. And let's say if we apply electrical current to the system for a period of time, then the amino acids should start to separate out on the glass slide. So let's have a look. So before electricity is applied, we can see here at pH 7, these are the ions that exist at pH 7. So for glycine, it will look like this. For lysine, it will look like this. and for glutamic acid, it will look like this. Okay, so these are just the formulas of some of these amino acids. Don't worry about the formulas of these. It's just kind of showing you what happens here. So before electricity is applied, all the amino acids are mixed together in this pH 7 solution, and it sits in the middle of the slide. You've got your positive and negative terminals at the sides there. So after electricity is applied to this solution, then glycine is neutral at pH 7, so it doesn't move when electricity is applied. You can see you've got one positive, one negative. It's a neutral molecule, so whether you apply positive or negative, it isn't going to move. Okay. Lysine, though, you can see overall has a positive charge. You've got two positives there and one negative, whereas glutamic acid has a positive and two negatives. So you could probably work this out. Lysine, there we are, has the overall positive charge, as we've seen there. So that moves towards the negative terminal. So you'll start to see lysine move across to this side. And obviously glutamic acid, which is this one here, has an overall negative charge. And this obviously moves towards the positive terminal. So really, we're just looking for the charges on here and seeing which way it's actually going to shift. So a mixture of protein fragments, so your peptides, as we've seen before, these can also be separated using electrophoresis. So it's not just amino acids that can be used. So your protein fragments are separated by the charge that they have at a specific pH of the buffer solution that they're in. So that's just the same as amino acids. They also have this charge. So another way in which they're separated as well is by the size of the fragment or the molecule. So, and obviously the size of it will impact the speed or the velocity at which it will move. And this velocity is actually proportional to the voltage that's applied to the plate. Okay, so your smaller molecules or your smaller fragments will move a lot faster than the bigger ones at a fixed voltage, which is quite obvious. If you've got a bigger fragment, it will take a longer period of time at a certain voltage compared to smaller fragments. So you'll start to see that kind of separate out on the plate. It also applies to branched molecules as well. So if you've got a molecule or a fragment with large branches, they obviously move a lot slower. They've got bits and pieces sticking out of them. They're going to kind of drag themselves along the plate. And your straight chain molecules will obviously will move a little bit easier. They don't have as many bits sticking out of them. Obviously, we keep this fair and we say that both fragments have the same mass, but obviously the one with the branching will just take that a little bit longer. So again, it's another way electrophoresis can be used to separate these different components out. Okay. And that's it. So that's everything you need to know for nitrogen compounds. Hopefully that was helpful. Like I say, the full range of A-level videos for CIE is available on Allery Chemistry YouTube channel. Please hit the subscribe button to show your support for this project. That'll be absolutely fantastic. Like I say, these are available to purchase as well. If you click on the link in the description box below, you'll be able to get a hold of them there. Great for kind of notes for your files, and you can write on them and annotate them as well to try and get that top grade in chemistry. Right, that's it then. Bye bye.